Lasso statistics. In statistics and machine learning, Lasso least absolute shrinkage and selection operator, also Lasso or Lasso, is a regression analysis method that performs both variable selection and regularization in order to enhance the prediction accuracy and interpretability of the resulting statistical model. It was originally introduced in geophysics and later by Robert Tibshirani, who coined the term. Lasso was originally formulated for linear regression models. This simple case reveals a substantial amount about the estimator. These include its relationship to ridge regression and best subset selection, and the connections between Lasso coefficient estimates and so-called soft thresholding. It also reveals that, like standard linear regression, the coefficient estimates do not need to be unique if covariates are collinear. Though originally defined for linear regression, Lasso regularization is easily extended to other statistical models, including generalized linear models, generalized estimating equations, proportional hazards models, and estimators. Lasso's ability to perform subset selection relies on the form of the constraint and has a variety of interpretations, including in terms of geometry, Bayesian statistics, and convex analysis. Lasso is closely related to basis pursuit denoising. Motivation. Lasso was introduced in order to improve the prediction accuracy and interpretability of regression models. It selects a reduced set of the known covariates for use in a model. History. Lasso was developed independently in geophysics literature in 1986, based on prior work that used L1 backslash display style backslash L1 penalty for both fitting and penalization of the coefficients. Statistician Robert Tibshirani independently rediscovered and popularized it in 1996, based on Brayman's non-negative garrote. Prior to Lasso, the most widely used method for choosing covariates was stepwise selection. That approach only improves prediction accuracy in certain cases, such as when only a few covariates have a strong relationship with the outcome. However, in other cases, it can increase prediction error. At the time, ridge regression was the most popular technique for improving prediction accuracy. Ridge regression improves prediction error by shrinking the sum of the squares of the regression coefficients to be less than a fixed value in order to reduce overfitting, but it does not perform covariate selection and therefore does not help. Lasso achieves both of these goals by forcing the sum of the absolute value of the regression coefficients to be less than a fixed value, which forces certain coefficients to zero, excluding them from impacting prediction. This idea is similar to ridge regression, which also shrinks the size of the coefficients. However, ridge regression tends to set far fewer coefficients to zero. Basic form: least squares, orthonormal covariates, correlated covariates, general form, whole form, interpretations, geometric interpretation, making L easier to interpret with an accuracy-simplicity trade-off. Bayesian interpretation. Just as ridge regression can be interpreted as linear regression, for which the coefficients have been assigned normal prior distributions, Lasso can be interpreted as linear regression for which the coefficients have Laplace prior distributions. The Laplace distribution is sharply peaked at zero, its first derivative is discontinuous at zero, and it concentrates its probability mass closer to zero than does the normal distribution. This provides an alternative explanation of why Lasso tends to set some coefficients to zero while ridge regression does not. Convex relaxation interpretation. Generalizations. Lasso variants have been created in order to remedy limitations of the original technique and to make the method more useful for particular problems. Almost all of these focus on respecting or exploiting dependencies among the covariates. Elastic net regularization adds an additional ridge regression-like penalty that improves performance when the number of predictors is larger than the sample size, allows the method to select strongly correlated variables together, and improves overall prediction accuracy. Group Lasso allows groups of related covariates to be selected as a single unit, which can be useful in settings where it does not make sense to include some covariates without others. Further extensions of Group Lasso perform variable selection within individual groups, sparse Group Lasso, and allow overlap between groups, overlap Group Lasso. Fused Lasso can account for the spatial or temporal characteristics of a problem. Lasso regularized models can be fit using techniques including subgradient methods, least angle regression (LARS), and proximal gradient methods. Determining the optimal value for the regularization parameter is an important part of ensuring that the model performs well. It is typically chosen using cross-validation. Elastic net, Group Lasso, Fused Lasso, Quasi-norms and bridge regression. Adaptive Lasso. The adaptive lasso was introduced by Zhu in 2006 for linear regression and by Zhang and Liu in 2007 for proportional hazards regression. Prior lasso. Computing lasso solutions. The loss function of the lasso is not differentiable, but a wide variety of techniques from convex analysis and optimization theory have been developed to compute the solution's path of the lasso. These include coordinate descent, subgradient methods, least angle regression (LARS), and proximal gradient methods. Subgradient methods are the natural generalization of traditional methods, such as gradient descent and stochastic gradient descent, to the case in which the objective function is not differentiable at all points. LARS is a method that is closely tied to lasso models, and in many cases allows them to be fit efficiently, though it may not perform well in all circumstances. LARS generates complete solution paths. Proximal methods have become popular because of their flexibility and performance and are an area of active research. The choice of method will depend on the particular lasso variant, the data, and the available resources. However, proximal methods generally perform well. Choice of regularization parameter. Selected applications. Lasso has been applied in economics and finance, and was found to improve prediction and to select sometimes neglected variables, for example in corporate bankruptcy prediction literature or high-growth firms prediction.